All right, these are the recorded office hours for November 29th, and I've received several questions, primarily on homework problems 3, 4, and 5. So I'll start there. So this is number 3. So you're told that you have a 6-pole, 3-phase induction motor being driven at 60 hertz. So the electric frequency going in is 60 hertz. So omega sub E is going to be 2 pi times that 60 hertz, or Fe is going to be 60 hertz. And you're told that your number of poles is 6. Then you're told that when connected to a load, it outputs a certain amount of power. Negligible rotational losses, so we can neglect those, while rotating at a speed of 1070 RPM. What is the slip? Well, the first thing we have to do, we have to find the synchronous speed. And so the synchronous speed, of course, is given by 120 times electric frequency divided by the number of poles. So we can find that. Then we know that the slip is going to be equal to omega s minus omega m all over omega s. We're working radians per second. This is actually in RPM, and so the other form, of course, would be ns minus nm all over ns, which makes more sense because I'm telling you that the motor speed is in 1070 RPM. So this is the one that you want to use. And using that, you can find the slip. And then when connected to a load, outputting 2 kilowatts of power, assuming negligible rotation losses for rotating speed since 1070 RPM, what is the developed torque? Well, we know that the developed power, is going to be equal to the developed torque times the speed in radians per second. So we need to convert the 1070 RPM into radians per second, divide 2 kilowatts by that speed, and that will give you the torque. Now we have a new load, so new load means new torque, which means new speed, which means new power. So the 2 kilowatts no longer applies in part C. Cannot use the 2 kilowatts. So we have a new load, new torque. What is the new speed of the motor in RPM? So since everything's changing, you cannot use the 2 kilowatts. And what you have to use is the fact that the torque and slip are proportional. So we know that the torque developed 1 over the torque developed 2 has to be equal to slip 1 over slip 2. So you have your torque you found in part B here, you have your slip you found in part A here, and you have your new torque you found given in part C here, so that allows you to find your new slip. And once you have your new slip, you can find your new speed. And so you make use once again of that they are proportional. Now in part D, for problem 3, you assume a value of a slip is 0.09. What electrical frequency is needed to have the motor rotate at a speed of 1070 RPM? So now I tell you what the slip is, and I tell you what the speed is. And you know from the formula sheet, Nm is going to be equal to 1 minus s times n sub s. So you know the slip, and you know the speed that you want. You want it 1070. And so from this, you can find out what your synchronous speed needs to be. You can find out what your n sub s needs. And remember, n sub s is going to be equal to 120 times the electric frequency, which you're trying to find, all over the number of poles. Number of poles does not change. And from here, you can figure out what your electrical frequency needs to be in order for it to have that speed with that slip. And so that's how you would solve for problem 3. Problem 4, you have a 3-phase induction motor driven at 50 hertz. Initially, the motor is connected to a mechanical load that requires 1800 watts of power. While connected to this load, the motor spins at 1300 RPM. Notice I don't tell you the number of poles. So the very first thing, part A, is we have to determine the number of poles. And we can get there because we know that n sub s, which is going to be equal to 120 times, in this case, 50 hertz, divided by P, is your synchronous speed. And this has to be greater than your n sub m, which is given as 1300 RPM. And we want the slip to be as small as possible. So we want the value of P that will give us a synchronous speed that's as close as possible to 1300 RPM, but slightly greater than it. Once you have your synchronous speed identified based on the number of poles identified, you can then find the slip, which once again, the slip is going to be equal to ns minus nm all over ns. And so that's part B. What is the torque supplied? Well, I tell you the power. And so once again, just like I did on problem 3, we know that the power has to be equal to the torque times the speed in radians per second. So I need to translate that 1300 RPM into radians per second, and then that will allow me to then find the torque. Now part D, I have a new load connector that requires 2000 watts. So here's part D. So new load, that means new speed, new power, everything's changing. But I do tell you it's operating in its normal operating range. That means that it's operating at small slip, which also should tell you that somewhere in here I'm going to have a quadratic, because usually when I start saying things like that, that means there's a quadratic, and indeed there is. And so what do we know? Well, we know that, once again, go back to the original equation, the developed torque, torque 1 over torque 2 has to be equal to slip 1 over slip 2. But I don't know torques. I only know power. So I have to translate this into an expression for power. And so to do that, I'm going to multiply this by some omega m1, and this by some, or actually, let me back up. Let me do it the other way. So what is the relationship of power 1 to power 2? Well, how is that related? Well, what is power? Well, this is going to be torque developed 1 all over torque developed 2 times omega m1 all over omega m2. Well, how are the speeds related? Well, we know from the formula sheet that omega m, I'll call omega m1, has to be equal to omega sub s, the synchronous speed, times 1 minus s1. And conversely, omega m2, the motor speed at a different slip, is going to be equal to omega s, because the synchronous speed doesn't change unless I change electric frequency, times 1 minus s2. So if I take their ratio, omega m1 over omega m2, then that has to be equal to, well, the omega s's cancel, 1 minus s1 over 1 minus s2. And so I can plug this in and relate then that my power developed 1 over my power developed 2 has to be equal to 1 minus s1 over 1 minus s2. There's my speed terms, times my torque. Torque developed 1 over torque developed 2. But the torque 1 over torque 2 is just going to be given by s1 over s2. So I can plug that in as s1 over s2. And so then I have everything that is known except the second slip, except the s2 term, which will in fact end up being a quadratic. So if I plug that in, that's 1 minus s1 over 1 minus s2 times s1 over s2. So here, obviously s1 is known. Down here I have an s2 times an s2 squared. And so I'm going to end up with a quadratic in terms of s2, which I can then solve for. And I pick the one that's the smallest value of slip because I want to be in the normal operating range. And once I have my value for s2, I can use that then to find my speed. So that's how I do problem 4. So moving on to problem 5. We have 83 hertz three-phase induction motor is running at 1537 RPM when under full load. Determine the most likely slip. Well, once again, part A, very first thing we have to do is we have to determine the number of poles. So we want our N sub S to be greater than NM but close to it. So I try different values of the number of poles until I end up with an NS that's greater than NM but close to it. So I try 2, 4, 6, 8, and so on, because the number of poles has to be even. Once I have done that, then I can use my equation for the slip to get to the slip. Now we want to determine the most likely speed if the load torque drops in half. So once again, we're going to make use of torque developed 1 over torque developed 2 is going to be equal to S1 over S2. So I have a change in the torque. That's going to result in a change in the slip. I can use that then to find my new slip. And once I find my new slip, then I can find the new speed. And so that's how I do problem number 5. And so those were the questions that have been emailed to me thus far.